Well, glad to be here again at this great series of meetings. So I'll talk about some recent work on vectorized Laplacian. So what's vectorized Laplacian? Actually, another name we have been using in earlier work dealing with the buckyball when it first came out. We called graph gauge theory. But for this audience, we can see the connection is actually quite useful for dealing with these new directions, dealing with high-dimensional data sets and with various applications. So, but the buckyball is sort of a nice shape. Usually, you might have a lower dimensional manifold of a pretty shape, and it is certainly quite pretty. It's a Cayley graph of A5. That's why you have 60 atoms. And here is the permutation alternating group A5, and you see the labeling of the vertices by permutations. The reason it is so nice and symmetric and so pretty is that we can use a lot of tools to break the matrix up into little blocks and then give us very nice solutions according to Frobenius for eigenvalue and for these vibrational spectrum. But in particular, one thing playing a key role is the discrete Laplace operator, which you can write it like this, summing over all its neighbors, and sort of the analogy of the classical Laplace operator. See, usually when we have a graph and adjacency matrix, the operator, your matrix as operator is acting on the space of functions, which means every vertex has one value. However, in many situations, we really should take a more general point of view. Our x can be anything, actually, assigning to each vertex something. Well, for example, for the vibrational mode spectra of molecules, it's every point happens to live in a three-dimensional space. So our Laplace operator is really 60 times 3, so it's 180 dimensions. Versus the recent work that I found out the relation, among many others, the X is a d-dimensional space. So, so it's a sort of a pretty classical setup. So at each node, we have vector bundles, right? And connec-tion is actually a well-used math term, which are rotations among the vector bundles, and you can rotate it back. So in the vibrational mode, these rotation really tells you how the spin rotated. So with that setup, this is sort of a quick way to compute the vibrational mode because your buckyball is not really so perfectly shaped. There's something called vibration. So that if you write it up as a potential function and solve it using these laws, then you can see these operators come up with higher dimensions. And that was what we used at that time to compute the vibrational mode and really see the colors there. So at each vertex, you have vectors, so that's the selection. If your connec-tion is very nice, especially working on the buckyball, if it satisfies some very nice symmetry described by groups, then there are many very nice consequences. The consequences is that all your connec-tion, which is vectorized Laplacian in my point of view, really breaks up very beautifully, have beautiful structure, which is sort of the old story at that time for the buckyball. But right now, in this new situation, for each data point, we want to make it into represent the data after compaction or whatever. And from one data point to another, there's a rotation and forming the connection network. So I was have some collaboration and interaction with Amit Singer's group at Princeton. So what they do, they got these medical data and using various ways to make it into vector of in RD, okay? And then there are these rotations, because very often, so this is a view graph borrowed from Amit. Actually, several view graphs borrowed from Amit. Example, you can see that you take all these random samples and you want to patch it together to get your picture. So, and this is his also. You can see these rotation, actually, some of it are real rotations. But when you take all these experiments, a lot of them are noises and errors. So there's a lot of noise in the data that you want to get rid of in order to uncover the beautiful manifold probably hidden there, right? Lower dimensions. So see, a lot of data is really noisy. And if you do it right, eventually you can uncover the real shape, okay? So in particular, if it's consistent everywhere, then we want to recover our shape, right? So one way to do it is to define this vectorized Laplacian. And so it looks very similar like the usual Laplacian and its potential Dirichlet sum, except everything with all the FUs are vectors, O's matrix rotation, and then we take the L2 norm. So, and for these consistent, it's a couple of equivalence relation for consistency. So, in fact, in general, this vectorized Laplacian doesn't have eigenvalue 0. Okay, if it has eigenvalue 0, then it must have eigenvalue 0 with multiplicity d, which is the dimension. And if that is the case, all eigenvalues will have multiplicity d. I didn't exactly define, I put a little bit definition later. It's actually this vectorized Laplacian is symmetric, so we can talk about eigenvalues. That's one step we have to say. And for any two vertices, different paths, it will be consistent when you do rotation. That's why we call it consistent. In that case, we can uncover the manifold by assigning the right direction to each node. So, and end up, you can construct the right shape at the end if it is consistent. There's a couple methods that we use. In fact, there's a new paper of Singer and Spielman. They also using eigenvalue to do this construction. So in general, so when it's consistent, it's all very nice. But what happened? Your data contain lots of noise, which is usually the case. So several approaches. So please cut me off if I go over. And I'm just going to talk about several general approaches, and each one has its merit, and in fact, they help each other. So random connection Laplacian. So usually we talk about random graph model. So this is a very general one. For every pair of nodes, you flip a coin according to a probability, Pij, okay? And assuming they are all independent random variables, indicator variables. With this probability, it's 1, otherwise it's 0. So it's a indicator random variables. And usually Dirichlet model is a case that all the probabilities are the same. That's GMP model. So what we want to do is really treat the matrix as a random variable. Sort of this approach have been developed by many people, but they usually look at Gaussian distribution, many others distribution. So we try to do is to get a clean version just for graphs. So we can clean it up and do the best we can for graphs. And it's actually very powerful in a way because I'm treating this random matrix as a random variable. And if I sum up so many of them, m of them, I would like to get a Chernoff type of inequalities in terms of the variance. Here, I'm always taking the spectral norm. Remember, all these are matrices, and the norm is the spectral norm. Well, if I do that, I'm almost getting the same Chernoff inequality, except here the dimension of the matrices came through. Okay, so what's the consequence of this? This says, okay, I have my random graph, and I have an expected adjacency matrix. So for example, for the Discrete graph, the expected adjacency matrix is very simple. It's P everywhere, okay? So this graph, it's very easy to compute eigenvalues, but I can bound my eigenvalue, all eigenvalues, with probability 1 minus epsilon. All the eigenvalues are very close to their associated eigenvalue, with a bound which depending on a few things. And the same thing for the Laplacian, but has a little bit stronger correlation. So in this case, if we really do it more carefully, in order to say this very well, in order to see if you have a lot of random noises, you expect the expected value, they are going to cancel out to be 0, right? Then you're going to get your very beautiful shape. You're going to get your consistency graph. However, this inequality tells you the variance is in your way. Okay, how will you decrease the variance in order to get rid of those noise in your data? So how do we get rid of that? Or attempt to get rid of a good amount of that? So there are a couple of other ideas, okay? One is graph sparsification. Instead of very big, complicated graph, it has been a pretty many work done. In sparsified graph, you take very few edges, but it preserves all the cuts. Okay, the Chigger ratio is about the same. Chigger ratio is the number of edges crossing versus the volume of one side. So basically, you preserve all the cuts. That's a very strong thing. So how do you do that? One way is to sample. However, you have to sample very carefully. If you treat all the edges the same, this dumbbell graph, all pairs are here, all pairs there. If you treat all the edges equally, if you only pick small number of edges, like n log n, you're not going to ever pick this cut edge. You're never going to preserve the cuts. See, you all really have to rank the edges. So we really have to tell difference between different edges in order to get rid of noises. We have to rank the edges. So here, how do we rank? The page rank algorithms. But the usual page rank is ranking vertices. How important is each website, right? That's how some companies around here got very well known for. Okay, the names was named for the search engine at Google. And basically, it has two parameters. One is sort of a jumping constant controlling diffusion and a seed. The original page rank, the seed, is with certain probability you go to a random page, and with certain probability you go to a link page. So that's the one of the original page rank, but you can choose arbitrary seed, get personalized page rank. But in a way, it's really is discrete Green's function. So when you have your Laplace operator, okay, you get spectral decomposition and you have Green's function, the general generalized Green's function really has this extra parameters here, which basically is page rank. If we do that and combining with a little bit electrical network theory, I think we are running late, so I'm going to skip this part. Basically, you can make it work so according to these rules, but adding all these adjusting constant, which is actually playing a very important role in controlling cluster when we do the partitioning algorithms. Then the effective resistance, the generalized effective resistance basically are these coming out from PageRank. So you can use PageRank, which can be computed, approximated very fast to do the edge ranking. And we can do the vectorized version of it. Here you just have to take the norms because we're going to have vectorized forms. But nevertheless, you can define these vectorized PageRank and vectorized Green value for the effective resistance for each point, for each edge, and we're going to use that to do the sampling subroutine, which is at the heart of sparsification, also at the heart at our algorithm for reducing the noises. I want to, let me see, almost make up for that. Okay, so there are, you combine these methods, once you get the edge ranking, can go back to here and here because you can use it. All the edges are different now with a rank. Then you have your pick and choose in order to try to see if you reduce the variance, if you reduce the, you're getting close to the consistency graph because we actually have this potential function, the Dirichlet form for evaluation. I also done some recent work on so-called graphlets, which is the spectral version for doing graph limit. If you know the limiting behavior, then your manifold probably should pop out minus the noises. I think I'm just going to end by mentioning some more applications. Since then, I keep on going to talks and kept on finding more and more application for these vectorized Laplacian. So for example, when you want to deal with large number of pictures, and they are, I think some people say billions of them now out there nowadays, possibly. How do you find these consistent paths? How do you get through the box? There are many methods people use for detecting features to reduce it into vectors to make the connection graph. Okay? And there's a building roaming one day that they actually really have the actual rotation. So I stole their pictures on the web. Okay. Oh yeah, wait a minute. Well, anyway, I didn't quite show the one that they're really using it to build a beautiful shape. I think this is all. I think I will stop here and thank you for your attention.